Hi there, Mr. Sutton here with the BC Calculus 712 Extra Practice Number 1 solutions on limit comparison test. On this problem, we want to know which of these 5 series converges, and it's just going to be one of them. So let's go through and see what we can eliminate. So for choice A, if we take the limit of this thing as n approaches infinity, we see that this ends up being 3n over n, which is just 3. That's not 0, so this one actually fails the nth term test and diverges for that reason. Moving on then, B, C, and D, if you look at them, they're all kind of similar. To do all of these, we would have to do some kind of comparison series. So we could compare all of these to either n over n squared, or, in this last case, D, n squared over n cubed. Now the reason I lump D in with B and C is all of these comparison series reduce to 1 over n, which we know is the harmonic series which diverges. So because we're comparing these to the harmonic series, because they're so close to that one, these all probably diverge as well. I haven't conclusively proven it yet, but we're going to take a look at choice E before we go back and dig into any of these, because these are probably dead ends. So E now, for that one we're going to use a comparison series of n squared over n to the fourth, which reduces to 1 over n squared. That's a p series with a p-value of 2. Since that's greater than 1, that means this is going to converge by the p-series test. So now to use the comparison here, should we use direct comparison or limit comparison? Well, it looks like both the numerator and denominator are bigger than the comparison series. So it's kind of ambiguous if you try direct comparison. Let's do limit comparison to be on the safe side. So I know that the original function here is positive. So is the comparison series 1 over n squared. And those are going to be positive for n greater than or equal to 1. Not much trouble on that. So now let's go ahead and take the limit as n approaches infinity of my original series over my comparison series. Let me change flip this to simplify my fraction. So I've got 3n squared times n squared in the numerator, and that's 3n to the fourth. Denominator, we have n to the fourth plus 2n times a 1, so no big change down there. And as n approaches infinity, I can forget about this lesser term of 2n. So it's really just 3n to the fourth over n to the fourth, which gives me a limit, if we cancel out those n to the fourths, of 3. 3 is a positive finite number. It's an L that's between 0 and infinity. Therefore, because the comparison series converged, that means this series converges as well by the limit comparison test. So we've conclusively proven that E converges. We don't have to test anything else out, so choice E. For this problem, we're trying to figure out which statement about the series 1 over 2 to the n minus n is true. Choice A, series diverges by nth term test. Let's take the limit of this function as n approaches infinity. If we do that, we can ignore this slower growing minus n term in the denominator. 1 over 2 to the n is a bottom heavy function, which means 0 is our limit. So this is a no. Our series may actually converge because we got 0. Going down to choice C, I'm going to skip to C because C kind of states the opposite of A. It says the series converges by the nth term test, and although we got 0, that is not enough to show that we converge. Nth term can only prove divergence, cannot prove convergence even if you get 0. So that leaves us with choices B and D. So for B and D, we're looking at limit comparison of this series with two different series. So in order for any of these to work, we need to verify that we have positive functions for each of these. So my original series, 1 over 2 to the n minus n, that's going to be positive. The harmonic series is going to be positive. And 1 over 2 to the n, that will also be positive if we pick any n values of 1 or greater. So moving on then, and actually trying these tests, let's do choice B first. So comparing to the harmonic series, 1 over n, since this is the harmonic series, we know that it diverges. So let's go ahead and divide the original series by the harmonic series and see what happens. So I've got the limit as n approaches infinity of the original, 1 over 2 to the n minus n, over the harmonic series, 1 over n. Same change flip to simplify this fraction. We've got n over 2 to the n minus n. As n approaches infinity, this is a bottom-heavy function, so this is going to go to 0 for the limit. And since this is not a positive finite number, since this is 0 actually, the limit comparison test is inconclusive in this situation. So we're going to go on and try out choice D now. In this one, we're comparing to 1 over 2 to the n. This is a geometric comparison series. It has an absolute value of its common ratio of 1/2. Since that's less than 1, this is going to converge by the geometric series test. So now, putting that in our n approaching infinity limit ratio here, we've got 1 over 2 to the n minus n over 1 over 2 to the n, this series here. Same change flip on this one as well. We've got 2 to the n over 2 to the n minus n. As n approaches infinity, we can again forget about this minus n. So it's just 2 to the n over itself, which gives us a limit of 1. Since 1 is a finite positive number, an L that is between 0 and infinity, that means that since the comparison series converged, the original also converges by the limit comparison test. So that's going to give us answer choice D. For this problem, we want to figure out if this series converges absolutely, conditionally, or not at all. We start by testing absolute convergence. So let's rewrite this without this alternating in the numerator. And this series right here, this is pretty close to 1 over the cube root of n, so we're going to compare it to that series and see what happens. So this new series here, this comparison series, we have a p series. This is going to be a p-value of 1/3, the exponent on the n here. Since that's less than or equal to 1, we see that this comparison series diverges by the p-series test. Now, comparing this to the original, since we have diverging and the original is less than this, a direct comparison is not going to work out very well, so we'll do limit comparison instead. So I have to verify that everything is positive. I'm going to say that my original is positive, my comparison series is also greater than 0, and this is going to hold true as long as n is greater than or equal to 1. Okay, so let me take my ratio now. Limit as n approaches infinity of the original over the comparison series. Same change flip. We've got cube root of n over cube root of n plus 1. As n approaches infinity, I can forget about this plus 1. So it's just cube root of n over itself, which is just 1. And since my limit is a finite positive number, an L between 0 and infinity, that means that since the comparison diverged, my original will diverge as well by the limit comparison test. So this is just the actual absolute value version of my function. It's not the original function, not the original, just the original absolute value version. So we still have to test the original for conditional convergence. Looking back at the original then, we see that it does alternate, and it decreases in absolute value to 0 because your denominator is growing while your numerator doesn't. So because our original terms are alternating and decreasing in absolute value to 0, we can say that the original converges conditionally by the alternating series test. For this problem, we want the interval of convergence for this series. Since this is not quite geometric, we need to go ahead and use the ratio test. So I have the limit as n approaches infinity, absolute value of, and now we have the n plus 1th term over the nth term. So n plus 1 x to the n plus 1 over 4 to the n plus 1, and then n plus 1 squared plus 1, whole bunch of n plus 1s up there. Craziness, right? Down here we just have this stuff cut and pasted. So now same change flip to simplify our fraction, or at least get there. So we've got n plus 1 times x to the n plus 1, and we're multiplying that by 4 to the n times n squared plus 1. That is all in our numerator. Denominator, we've got all this stuff here times nx to the n. Time to cancel out what we can. X's cancel a little bit, so I'm just left with an x to the first power in the numerator. The 4's also cancel, leaving me with just a 4 in the denominator. So I've got an n plus 1, I've got an x, which I'll write the x before the n plus 1. And then I also have an n squared plus 1 up there. Down here, I have, let's see, a 4, I've got an n, and I've got all this craziness in here. So there was the numerator. There's the denominator. And I'm hoping I can simplify this a little bit more. So as n goes to infinity, this plus 1 in here goes away. So does this other plus 1. We can ignore it. This plus 1 in the squared parentheses is gone, so you have n squared plus 1. This other plus 1 is gone. So at the end of the day, we have an x, we have an n cubed in the numerator. In the denominator, we have a 4 and an n cubed. So this just becomes x over 4, canceling out those n cubes. To actually get an interval of convergence, I need to set this less than 1. And let me just multiply both sides by 4 to get it as simple as possible. So absolute value of x less than 4. Now to get a rough interval of convergence, let me just rewrite this without absolute value. So negative 4 less than x less than positive 4. But that's a big question mark because since we used ratio test, we have to test the endpoints. Geometric series test would have given us unambiguously less, strictly less thans, but we need to see if there's an equals on these. So let's say that x is negative 4. What does that do to my original series? So that would give me, let's see, n times negative 4 to the n over 4 to the n and all this other stuff here. But if you have negative 4 to the n over 4 to the n, you can really simplify that as just negative 1 to the n up here. So I'm going to have negative 1 to the n. I still have an n up there. I still have an n squared plus 1 downstairs. So this is a series that is alternating, and because it's a bottom-heavy function, it's decreasing in absolute value to 0. That means this is going to converge by the alternating series test. So this first less than should actually be a less than or equals. Now let's test the other endpoint, 4. So we've got a 4 to the n and a 4 to the n. Those are going to actually cancel, leaving us with just n over n squared plus 1. This is a series that we could figure out convergence for with a comparison. Let's compare this to the series n over n squared, which reduces to 1 over n. That's the harmonic series, so we know it diverges. And now let's just, before we rigorously prove limit comparison here, let's go ahead and make sure these are both positive. So this series here is definitely positive. So is the harmonic series. And this is true for n greater than or equal to 1, which is what I'm going to have to specify here. 0 is not going to necessarily cut it here. So now let me set up a limit as n approaches infinity of this original series divided by the harmonic series that I'm comparing it to. Same change flip. We have n times n in the numerator, so that's n squared. We have n squared plus 1 in the denominator. And as n approaches infinity, I can forget about this plus 1, so it's just n squared over itself, which is 1. Since I get a finite positive number, an L, between 0 and infinity, that means that since my comparison series diverged, my original also diverges by the limit comparison test. So at the end of the day, my interval of convergence then, we have negative 4 less than or equal to x because we converged at negative 4 by AST. And then we'll say less than 4 because we diverged at that other endpoint. For this problem, we're just trying to prove if this converges or diverges. So this is a good one for a comparison. I'm going to compare this to 1 over n squared because this is almost a p-series. Now 1 over n squared is a p-series, p-value of 2. Since that's greater than 1, we know this comparison series converges. Now in terms of which comparison test to use, here we have a smaller denominator and a larger numerator. So the original is actually bigger than our comparison series, which isn't very good if you're trying to prove convergence. So let's use limit comparison instead. I can verify that my original here is a positive number, and 1 over n squared is a positive number if n is 3 or greater. Because if it's 2 or less, then we're going to have a negative in the denominator. So for n greater than or equal to 3, these functions are positive. So let me set up my limit now as n approaches infinity, and we'll have the original 2 over n squared minus 5 divided by the comparison series 1 over n squared. Same change flip to simplify this a bit. We have 2n squared in the numerator. Denominator is just n squared minus 5. As n approaches infinity, this minus 5 goes away. We just have 2n squared over n squared, which is just 2. Since that's a finite positive number, a number in L between 0 and infinity, and since my comparison series converged, that means this original series must also converge by the limit comparison test. For this problem, we want to know if 1 over 10n minus 1 converges or diverges. Now this is a series that is pretty similar looking to 1 over n, so I'm going to compare it to that. And 1 over n is a good one because this is the harmonic series. We know this diverges. So I'm looking to prove that this thing diverges as well. So to do this, I need to figure out which comparison test I'm using. Since this one, it's not really clear whether this is a bigger or smaller series than 1 over n, I'm going to just play it safe and use limit comparison. So to do that, I just need to make sure both of these series are positive. This original is definitely positive and harmonic is positive if n is greater than or equal to 1. So now let me take the limit as n approaches infinity of the original over the comparison series, the harmonic. Using same change flip to simplify my fraction, I have n in the numerator, 10n minus 1 in the denominator. As n approaches infinity, I can forget about this little negative 1, so it's really just n over 10n, which reduces to 1/10. And 1/10, that is a number that is positive and it's finite. It's a limit between 0 and infinity. Therefore, because my comparison diverged, 1 over 10n minus 1 also diverges by the limit comparison test. On this problem, I'm trying to figure out if this series converges conditionally, absolutely, not at all, which one of these? So I'm going to start by testing, as I always do, for absolute convergence. So we need to drop this negative 1 to the n plus 1. I'm also going to take the absolute value of sine of n over n squared, which I wouldn't normally do, but sine of n can be negative or positive, so we need to take that into account and make sure there's no negatives in here. All right, so how do I deal with this series? Well, sine of n hovers around 1, so I'm going to try comparing this series to 1 over n squared, because none of the other tests really do this thing justice. So compared to 1 over n squared, which is a p-series, p-value of 2, since that's bigger than 1, we know this series will converge. And which comparison test am I going to use? Well, sine of n can't be any bigger than 1. It's always going to be less than or equal to 1. And the denominator is exactly the same. So I'm just going to use direct comparison on this one. No need to go all out with limit comparison. So I can say 0 less than or equal to this absolute value series, which is less than or equal to 1 over n squared, because again, sine of n can't be any bigger than 1. So this means, and by the way, this is going to be for n values of 1 or greater. So this means that our series is going to converge because it matches whatever the behavior of the comparison was. This is going to converge, and it's going to converge absolutely by the direct comparison test.